new.
From the office.
Okay, I want to show you something new today. This is pretty cool. I can't pretend it's quite as cool as 3.4, but it's still pretty cool.
What was like the title of 3.4?
3.4?
Yeah.
3.4 was concavity and second derivative test, if you had to call it something. This we would call probably horizontal asymptotes and limits at infinity. Okay. So what we want to look at here is, you like that?
Wait. Why is it all fit?
No.
Because it's infinity. It's going to infinity.
Oh.
Okay, there we go. Okay, so now what if we look at something like this?
I'm good.
What if we look at something like this here? What if we take the function as a rational function? Well, let's define that first of all, because we're going to talk about rational functions in this section. A rational function is a function that can be written as a quotient of polynomials. Okay, so one polynomial in the numerator, another polynomial in the denominator.
Rational.
That's called a rational function. Yeah, rational as in ratio of polynomials. What we want to look at today is what's going to happen if we walk out very, very far in either the positive or negative x direction. What happens to the functional behavior? What does it do? Now, in a case like this, notice what happens. It's pretty active in here. It changes quite a bit. But then when we start scooting out towards positive infinity or negative infinity, it gets pretty boring. The function just ever more closely approaches the line y equals 3. Okay, so we call that a horizontal asymptote. Okay, that's as distinct from a vertical asymptote. Now remember where we had vertical asymptotes. Those were places where we had zeros on the bottom of a function and not on the top. So places where the function blew up. Horizontal asymptotes describe this kind of behavior where as the ant moves further to the right, he more and more closely is sticking to this line. He never actually gets to it, right? He never actually gets to y equals 3 in this case, but he gets closer and closer all the time. The further he is to the right, guaranteed, the closer he will be. Horizontal asymptotes, so the way we might say this then, I guess, is like this. We could say that the limit of f of x, if this is f of x, right, as x approaches plus or minus infinity in this case, the asymptote exists on both sides, is equal to, and we could write it in terms of the actual function if we want to, the limit of 3x squared over x squared plus 1 as x approaches plus or minus infinity is 3. That's the limit of our motion, that we're always approaching a value of 3 the further out we go. So we could say then that it's got a horizontal asymptote at y equals 3. Now, the function doesn't have to behave smoothly like this. It could even do something a little different. It could do something like this maybe. If we want to make our asymptote y equals 3 again, function could do something like this. Maybe it goes, it could do that. It could oscillate around the asymptote as long as the oscillations are dampened as you go further out to the right. The magnitudes are getting smaller. So it's still
get over.
No, you can't. That's an important point. You can't cross a vertical asymptote, but you can cross a horizontal asymptote.
Wait, what's the reason you can't cross it?
You can't cross a vertical asymptote because that's a place where that's a value of x where the function is fundamentally undefined.
Oh.
So you can't define the function there, so therefore you can't cross it. Now, a horizontal asymptote is different. A horizontal asymptote is merely saying that if we go very far to the right or the left, the function tends to that value. Doesn't mean it couldn't be above or below, but it just tends to that value, right? So in this case, this function that oscillates like this is going to intersect the line y equals 3 an infinite number of times. But over time, the oscillations are going to diminish, and so it's on average, it's going to be much closer to 3 out to the right than it is in here. Does that make sense? Okay. So it's just this guiding behavior. Now, the way we're going to use these things, when we're sketching a function, it's valuable for us to know the horizontal and vertical asymptotes because we can do things like this. If I knew, for example, that... Okay, let's say this. Okay, let's say we know here, for example, that we don't know anything about this graph, but we know that it's got a horizontal asymptote and maybe 2 vertical asymptotes. So it looks like, let's put them here. We've got...
Hey, can you go back to these?
Yeah, I will. I'll go right back to it. So there's one horizontal asymptote. Here are, let's say, 2 vertical asymptotes. Okay, if there are, so 3 total asymptotes, if we don't know anything else about the function, there might be some bizarre stuff going on, but we have the basic skeleton of that function's behavior just by using those asymptotes. It's really got to do one of these things. Over on this side of the vertical asymptote, it's either going like that or like that, right? In between, it's either doing this or it's doing that, right? To the right, it's either doing that or that. So there aren't that many different permutations of that behavior. You know, we have a basic idea with very little testing of points or concavities or whatever you want to do. We'd have a pretty good idea what this function's doing based on its asymptotes. Yes?
Can you go back to the...
Yeah, that's fine. I just want to show you why, in terms of a...
Do that?
Say it again.
Could it?
In between, yeah, it could. You're right. In between, it could do this too. Nolan makes a good point. It could go like this in the middle.
All the way around.
Okay, it could go like this also, or like this.
Oh, okay.
Right? Because the horizontal asymptote doesn't apply in the middle.
Right.
Right? The horizontal asymptote really is just out at the edges. Okay. So but we still were able to pin it down pretty well. So when we're trying to use this, when we get to section 3.6, which is where I think we're gonna break this chapter up. We'll go sections 3.1 through 3.6, and then take a test and get that out of the way, and then we'll move on to the applications, to optimization and some other more applied aspects of this calculus. But in 3.6, your whole goal is going to be you're going to be given a function, and I want you to be able to create a table and sketch it. You know, just based on, you want to get horizontal asymptotes, vertical asymptotes, first derivative critical number, second derivative critical number, so you can find extrema, inflection points, etc. And put all that stuff together and quickly sketch the graph. Okay, know what its behavior is. Okay, so you want to go back to here.
Yeah, that's what it is.
Okay.
Okay. Yeah, thanks, man.
Okay, Matt, questions on that? Okay, you just want to see it?
Yeah.
Okay.
I just wanted to see the graph.
Oh, gotcha.
Formula.
Okay. Okay, so now let's continue on down here. So then we could say,
Shoot.
okay, so here's sort of our, it's not a formal definition. This is still an informal definition, but we could say the line y equals L is a horizontal asymptote of f of x if either the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L. And a lot of times we'll talk about those as the tails of the function. The left tail is the behavior at negative infinity, towards negative infinity, and the right tail is what happens when we approach positive infinity. Okay, so what about here? Let's look at some examples. Now, what about this one? If we want to find the limit of this function, what do? As x approaches positive infinity, we can look at these two terms separately. The first term, 7, is constant. What about the second term? If we look at the behavior of this part right there, 3 divided by x to the 1/2. As x is approaching infinity, what's going to be happening on the bottom of that function? The bottom's getting small. It's getting big, isn't it? Because x to the 1/2 is a square root. So, for example, if x were 9, the bottom of the fraction would be 3. If x were 100, it would be 10. If x were 10,000, it would be 100, right? But the square root kind of slows it down a little bit. But still, if x is going to increase without limit, so is its square root, right? So the bottom of the fraction explodes. What happens to the overall magnitude of the function then if the top is staying fixed and the bottom is exploding? It's going to get small because we're as the bottom explodes, we're taking 3 pieces out of larger and larger holes, right? Make sense? And so that the fraction as a whole, then we could say, is going to go to 0, right? And in the limit, we can just get rid of that, and we know that the answer is just 7, right? Because the second term in the limit that x goes to 0, that term gets extinguished. It gets smaller and smaller and eventually vanishes, right? Does that make sense? Everybody's okay with that? Because that's really important. You got to get that part. You're gonna get the rest. That's a big one.
How many of us already on this?
Well, we have. I mean, this is sort of a rehearsal. But the reason I review that is because now we got to deal with a rational function, something like that. Okay, so what do we do? What do we do with this? If we want to find this limit, we're going to look at 3 examples, and then I want you to come up with a general rule for how we deal with these 3 kinds of examples. Each of these 3 examples we're going to look at is exemplary of a kind of rational function, a category of rational function that we'll be able to, in the future now, as a product of what we're doing right now, we'll be able to take these limits by inspection. We won't have to do any math at all. We'll be able to just look at them and tell what the answer is. But we got to do the legwork first. We got to figure out what kind of result we get here. So if I try to take this limit directly, it doesn't work, right? Because I can't be plugging in infinities. Infinity is not a number. If I were to try to let x approach infinity, wouldn't you agree that the top of this fraction, the numerator, is exploding and the bottom is too? And that's indeterminate. That's an indeterminate form of a limit. We don't know, and we'll get into this hopefully at the very end of the year. We'll talk about some more sophisticated ways of dealing with indeterminate limits. Limits that are of, for example, here's 2 of the many indeterminate forms. We would say that if I get an answer that is 0 over 0, we don't know. That's indeterminate. We have to do something to figure out what's going on. We dealt with limits like that earlier in the year, recall. In chapter 1, right, 1 and 2, we talked about what do we do in the case of limits that are 0 over 0. That was more work, and we had to either factor the top and factor the bottom and cancel factors, or we multiplied by the conjugate of the bottom if there was a square root. Remember, we had that rationalizing technique, or we combined, we got a common denominator. We did all kinds of things, all kinds of algebra. But we had to resolve this dilemma where we had 0 over 0. That's one kind. Another kind is infinity over infinity. That's indeterminate, right? We don't know what happens. It could be anything. It could be infinite. It could be 0. It could be a number. We don't know. And then another kind would be 0 times infinity. What wins? The 0 part or the infinity part? Who knows? It's indeterminate. So here's one of those many types. This is an infinity over infinity type. Okay, so what could we do algebraically? Anybody have any ideas what we could do with this? Algebraically, we've got to deal with that indeterminate form. Say it again. Well, honestly, you accidentally had a really good answer there. That's not what we're going to do. But later on in the year, that's called L'Hopital's rule, and that's what we will do, is differentiate the top and the bottom. And it works. It honestly does work. But we're not going to do that now. Why? Because we don't know that yet. That's chapter 7. We don't know that.
Oh, we can get ready.
No. There's a better way, easier way.
Get out of the fraction.
Okay, kind of. Now think what's causing the problems here. What's causing the problems is the x squared, right? In both the numerator and the denominator. It's the x squared term. That's what's exploding. So what if we were to factor out of the top and the bottom an x squared, right?
Well, you can do that.
So what's that going to give us? If we factor out, and I've still got a limit here. If I factor an x squared out of the top, what am I left with?
2 plus 5.
2 plus, not 5, 2 plus. Now factoring means I'm dividing it away from each term. So what am I left with if I divide an x squared away from 5?
5 over x squared.
5 over x squared. Okay, in the bottom, I'm going to factor out an x squared, leaving me with
3 plus 1 over x squared.
Okay, good. Now algebraically, what do we do with the x squareds?
Eliminate them.
We cancel, right? Now, we are changing things slightly there, but it doesn't matter in this case. Remember, we did this earlier in the year, and we said we're finding a function that agrees with the original in all but one place. Remember saying something like that? We're filling in the hole. Well, here, it's not a hole that we're dealing with. We're dealing with the tails of the function, and so nothing's really happening at x equals infinity, right?
Didn't that just make the...
So we can cross them out.
Didn't that just make the exponents more complicated with fractions?
No. You'll see why it didn't.
Okay.
It didn't. See, now those cancel algebraically, right? Okay, now if we take our limit, let's go ahead, I'm going to rewrite this. We can see this a little better. So we've got the limit as x approaches infinity of 2 plus 5 over x squared divided by 3 plus 1 over x squared. In the limit that x approaches infinity, you've already told me something important. Something like what we're seeing here. What happens to those terms? The 5 over x squared and the 1 over x squared as x approaches infinity. They go to 0. Yeah, they get extinguished, right? They're going to shrink to 0. So we're able to say this.
2 over 3.
Those go to 0, and what we're left with is simply a 2 over 3. We're left with a 2 on the top and a 3 on the bottom. Okay? So let's see if we can generalize that. If we're taking a limit of a rational function where the order of the polynomial on the top matches the order of the polynomial on the bottom, what is the order of the polynomial on the top? What do I mean by that?
Squared plus a constant.
So it's a second order then, right? The highest power of x in the polynomial. So if the order of the polynomial on the top matches the order of the polynomial on the bottom, then what could we predict as the result? We got an answer of 2/3. Where's that coming from?
Coefficients, divided by coefficients.
The leading coefficients. Yeah. So after we divide the x's away, the matching powers of x, we're just left with the naked coefficients, the leading coefficients, right? They go to 0 because in the limit, as x goes to infinity, the bottom gets huge, so the fractions disappear, right? And so we can see our answer right here,
Well, that's way
So-
easy.
right?
When they're the same order, you can do that. Just
When they're the same order, you know automatically that the limit at infinity, right, or negative infinity, is always going to be the ratio of the leading coefficients. Yes, sir.
What if one of the pluses was a minus?
It doesn't matter
Okay.
because I'm either adding or subtracting 0. Big deal.
So what if you had 2x squared plus, or 2x cubed plus something x squared? And
Okay,
something y
let's see. That's the next case we have to look at.
All right.
So case number 1 was, what if the orders are the same? Now let's take a look at a different case. Let's look at the case where the bottom is bigger. The order of the polynomial on the bottom is larger than the order of the polynomial on the top.
Would it just be 0?
So, yeah,
Winning.
yeah. And your intuition probably can tell you that because now we can even think about this in a very general way. As x is approaching infinity, look at the behavior of the numerator compared to the denominator. In the numerator, we're multiplying x's by 2. In the denominator, we're squaring the x's. So which is more aggressively running to infinity, the numerator or the denominator? The denominator, sure, right? Does that make sense? The denominator is because the denominator has a higher power of x. And so even though the numerator and the denominator are both approaching infinity, now you got to listen to this carefully. This is a little weird, but this is true. And we'll put some mathematical teeth in this. But the denominator is approaching infinity infinitely faster than the numerator, right? Because it's x squared. It's effectively numbers approaching infinity squared instead of just numbers approaching infinity, right? It is. It exactly is relative. Exactly. And so because the bottom is approaching infinitely faster, it wins the race. And it explodes faster, and so the fraction as a whole goes to 0. Now we can show that mathematically. We can show that by just dividing the, well, there's a couple ways we could do it. We could either divide top and bottom by x, or better yet, how about if we divide top and bottom by x squared? If we factor out an x squared from the top and the bottom.
That's a great idea.
Wait, say that again, sorry.
We're going to factor an x squared out of the top and the bottom and cancel them, and then see what's left. Well, I can factor an x squared out of any terms. I'm just dividing x squared away from those terms.
Okay.
So what am I left with then? Huh?
Why do we want to do that?
We want to do that so we can. So we're gonna see something analogous to this happening. Up here, we divided the x squared out of each of these two terms, and then after canceling the x squareds, look what we had left. We ended up with constants plus fractions with constants in the top and powers of x in the bottom. So when we let x go to infinity, these fractions are going to go to 0 because the bottoms get huge and the tops just stay the same. Right? The top is going to stay 5 in this fraction, but the bottom is going to get huge. So the magnitude of the fraction just diminishes. Okay, so then, so if we do that up here, if I factor out an x squared, what am I left with? What's the first term give me? 2 over x. If I divide 2x by x squared to get rid of that, to pull that x squared out front, I'm left with 2 over x, and then plus 5 over, just like before, 5 over x squared. In the bottom, I'm going to be left with 3x squared divided by x squared is just 3. Good. Plus 1 over x squared. So these guys cancel, right? The x squareds cancel algebraically. And then what we're left with here in the limit x goes to infinity, what's going to happen to 2 over x? Yeah, it goes to 0. 5 over x squared goes to 0. 1 over x squared goes to 0. What we're left with on the top is 0 plus 0 over 3. 0. Well, no, in the limit it is. In the limit, that's what it's approaching, right, is 0. So what we end up with then is, in the case, as predicted, in the case where the denominator is a higher order polynomial than the numerator, you know that you're going to get a horizontal asymptote at 0, so the x-axis, right? You always get a limit.
Is that 100% effective?
100%. 100%.
What?
If the denominator is a higher power than the numerator.
Oh,
Yep, always works. Always works. Okay, last example.
Definitely
Oops.
go to 0 on the bottom.
I guess I don't need this thing here, do I? No, let's get rid of it. Oh, yeah, I do.
Oh no! I'll read it now.
Oh, so.
No cheating. Can't look ahead. Okay, so what about this one then? What's going to happen? What's your prediction? In the limit,
Bottom's gonna be 0.
1.
bottom's going to go to 0. What's it? And the top is
1. 2. Not 1. 2.
infinity.
Infinity. Good guess.
Okay, so the top is approaching infinity infinitely faster than the bottom is. And so therefore the fraction, when the numerator gets big, the fraction gets big. And so this fraction is going to explode. Right? There is going to be no limit. There is no horizontal asymptote here. If we wanted to see, maybe we don't need to see the math. If I factored out, we can do it real quickly. If I factor out
We don't need to do it, but we'll do it anyway.
an x cubed, top and bottom, right? On the top, I'm left with 2 plus 5 over x cubed. On the bottom, I'm left with, 3 over x if I divide x cubed away from the first term, plus 1 over x cubed. These guys cancel algebraically.
Those fractions are kind of confusing.
Those go to 0, right?
The algebra.
We just divided by
I said 2.
Okay? And so what we end up getting is 2 over 0, which is undefined. Okay?
Yeah.
I actually made fun of you. I apologize.
Okay, so no limit.
Yeah, you know,
No,
you were
But
still
you remember
wrong.
me saying it.
But you were still wrong,
I was right. It's 2 over 0.
which is good.
All right.
No, there's no limit. Math is all relevant, or relative.
Okay, so then we end up, so we had some, we were able to resolve this into 3 rules. We don't have to do any of this algebra ever again. Now we can just look at the function and tell what's going to happen. So we know that if the degree of the numerator is less than the degree of the denominator, we know that
My pencil broke.
L equals 0, right?
Oh, yeah.
If the degree of the numerator is equal to the degree of the denominator,
The leading coefficient.
L equals the ratio of leading coefficients.
No limit.
And then finally, if the degree of the numerator is greater than the degree of the denominator, L does not exist.
You put your apostrophe in the spot.
What's that? Oh, you're right, I didn't.
There you go.
Okay? What's that? Sure. Too far?
Yeah.
Stop.
Stop there.
Wait.
Okay. So there's one more little wrinkle that we got to look at, but I don't want to do it today. Well, I'll let you work on this a little bit, and then we'll look at the other wrinkle maybe tomorrow. Yeah.
How many more wrinkles?
One in this stuff. One. That's it. There's one other weird thing to look at, but well, no, actually 2. Actually 2. 2 more specifics here. But I don't think I could get through them. I need a little more time to get through them, so I don't want to start.
Windows 8? When is that coming out?
Windows 8.
We have a beta.
Windows 8?
Developed the version out already.
Really?
Yeah.
It's just like the phone. It has like tiles.
Really?
Oh,
It's a total different interface.
Did you start ready soon?
Can I get rid of this?
No, not at all.
I'll put this one on the. I'll actually put a PDF of this on the notes too. How's that?
Okay, do you know?
Yeah.
Do you know?
It's a July 2012.
There's a laptop. I think the Chinese government makes it. It's like Lenovo or something like that.
Yeah, just-
Yeah, it's not made by the Chinese government.
What was it?
It's a good cheap laptop.
No.
Okay,
I'm
well, hold
probably
up.
saying
Let me do one example real quick, and then I'll turn this off. Okay, so tell me what this is then. I want to know if f of x equals 2x cubed plus 3x minus 11 over 7x cubed
2 sevens.
plus 3x squared minus 11x plus 17.
2 sevens. 2 sevens. 2 sevens.
What's our limit?
2 sevens.
Jump link. Okay, and so what we know, one thing I forgot to mention, one last thing. This works whenever you have a rational function. Both tails, this is important, both tails share this asymptote. I think in those examples I always had approaching positive infinity, but we didn't need to. It could have been approaching plus or minus infinity. Yeah, the same asymptote is going to be shared on both sides. So a single horizontal line is going to describe both of those behaviors of the tails. Okay. So that's all you have to do. I mean, that part is ridiculously simple. What we're going to look at, just so you're ready, what we're going to look at, the 2 other things we have to look at is what's going to happen when we see something like this. What if we have it, and take a guess. I'd like you to just see what you think about this. What does your intuition tell you? What if we want to take the limit of something like, I'll just take one out of the book. What if we're going to take one like this?
Wait, do I look older or younger with contacts?
Older.
Or the same?
I think it's the same age.
Yeah.
It's different.
What a coincidence! I am the same age. Well, I'm obviously getting older every second, but
You look like a new man.
You're definitely older than you were with your glasses.
this is true.
Got a fresh haircut. Contacts.
You need a flat top.
Yeah. We should all get flat tops.
Yes.
All those in-
Calculus flat
I'm
tops.
not cutting my hair.
You, Anna.
Oh.
It's a really long one.
Okay, what's gonna happen? What's gonna happen with that?
3 over for
Like a Slim Jim? Yeah.
Oh, yeah, can you grow a rat tail, please?
Dear God, no! Don't do that.
Awesome.
Okay, what's gonna happen with that? What do you think?
3 over
Now,
32.
what we can do here, just real briefly, is we could talk about, we can do this conceptually, and then maybe later we'll look at how we could show this mathematically. But we can get through this just by looking at this conceptually. Now, and there's an important thing going on here. As x approaches infinity, you know that whenever x approaches infinity, that the most powerful term in a function is always going to be the dominant term. So, for example, if I have a polynomial, and I'll demonstrate this for you, not today, but I will demonstrate this for you. If we have something like, let's say, y equals 2/3 x cubed minus 3x squared plus 11x plus 14. If I take the limit as x approaches infinity, the only part of that polynomial that matters a bit is the first one. Yeah, that's going to totally dominate the behavior. That's the dominant term because it's got the biggest power of x, right? And so if we apply that reasoning to this guy, then all we've really got to do is look at, in the top, the 3x, and in the bottom,
Square root of 2x.
exactly, the square root of 2x squared. So what's that going to look like? So that's going to look like, then, if we just focus on those parts, yeah, I'm going to get the limit of 3 over the square root of 2 is going to be the constant part, right? But then look at the variables. Here's the part that's a little tricky. On the top, I've got an x. On the bottom, I've got a square root of x squared. But what's the square root of x squared defined as? Well, what's that? Think about what that's doing. The square root of x squared. X squared is always positive. It's absolute value. The x squared is always positive, and its square root is so it does. It does affect the absolute. The square root of x over x. Now think what that function's value is going to equal. If we just focus on that part, what is the square root of x over x?
That's the first infinity, as long as it's not negative infinity.
I mean, not the square root of x. I don't mean to say that. Just x over the absolute value of x. I said that wrong. Okay, what's that going to be if we look at this as a piecewise function? What's that going to be when x is positive? What is the absolute value of x equal to when x is positive? Just x, right? So x over x would equal 1, right? What's that going to equal when x is less than 0? If x is negative, what is the absolute value of x equal? No.
The absolute value of
1.
x.
0.
The absolute value, if x is negative, the absolute value of x, in order to be positive, must be negative x, right? So x divided by negative x is negative 1, right?
Say that again.
Yeah.
I didn't make any
Okay,
sense.
okay, let me say that again. The absolute value of x by itself is always defined as this. It's x when x is positive and
Right.
negative x when x is negative, right?
Yeah.
Because I have to multiply the negative by -1 to make it positive, right? That's the job of absolute value. So therefore, if I break this absolute value of x up into a piecewise function, I'm going to have two different behaviors. When x is positive, I just get the ratio x over x. That's 1. When x is negative, I get the ratio x divided by negative x, which is -1. And so truly, the graph of x over absolute value of x looks like this. Whoops. It looks like this. That's the graph of f of x equals x over the absolute value of x, or that, doesn't matter. Okay? So do you see that we're going to get a little different behavior here? We're going to get a little different behavior. What we're going to get is the 3 over the square root of 2 is the magnitude of the line, but it's going to be positive on the right side, negative on the left side. See?
Got it.
If yeah,
If the absolute value is at the top.
if I do that. Okay, it doesn't matter if the absolute value is at the top or the bottom. That's still going to give you the same result. But if I have a negative number out front, that's going to flip that thing around the y-axis. Okay, but we'll talk more about that later. That's one wrinkle we got to deal with.